So we're going to start with lesson 8, inference for one sample. And starting off that, we're going to start with one sample proportion. So if you remember, the central limit theorem states that if your sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. So when we're talking about proportions, we refer to this as the rule of sample proportions. So it really just states that if your sample size and your proportion agree with your assumptions, which is that you have at least 10 successes and 10 failures in your sample, then the sampling distribution will be approximately normal. So if all of your assumptions are met, then the sampling distribution will have a standard error of the square root of p times 1 minus p over n. Then you will use the normal approximation method for that. And on the other hand, if your assumptions are not met, then your sampling distribution is approximated using a binomial distribution, which we call the exact method. So confidence intervals for the normal approximation method for one sample proportion is used to after we know all of our successes and our failures. So you calculate the number of successes in your sample by taking your sample size and multiplying that by your p-hat. And then to calculate the number of failures, you just take your sample size and you multiply that by 1 minus your p-hat. So now you have your successes, now you have your failures. If they are not at least 10, then we cannot use the normal approximation method. So we want them to be at least 10 or greater so that we can use the normal approximation method. And the confidence interval formula for a normal approximation method is p-hat plus or minus z star times your standard error. And here your standard error is calculated by taking the square root of p-hat times 1 minus p-hat over n. So just something to remember is that the value of your z-star multiplier will depend on your level of confidence that you have, whether it's 99%, 95%, or 90%. And then your standard error is computed using p-hat, which is an estimate of p, which is your population parameter. So there's a way you can compute a sample size if you start with a confidence level and a margin of error. So it's kind of like working backwards if you think about it. So you can take the margin of error and the confidence level that you're given in order to find a minimum sample size needed to produce those results. So it's kind of like taking your end result, what you want that to be, and learning how big your sample size must be in order to get those results. So you can calculate this by, you need your margin of error and an estimated value of your proportion. So you would take z star divided by the margin of error and square that. Then multiply that by your estimated value proportion times 1 minus that same value proportion there. And then you'll get the minimum sample size needed. So if you are not given an estimated value of the proportion, you can always use 0.50 because it will provide the largest sample size calculation in order to get a minimum sample size given a confidence level and margin of error. So here's an example of computing a necessary sample size. So if you want to construct a 95% confidence interval for a certain population proportion with a margin of error equal to 4%, then we will need to calculate a sample size in order to get those results that we would need. So here we're not given an estimated proportion, so we're going to use an estimated proportion of 0.50 like I mentioned before, because it's just a conservative estimate of a proportion. So just a reminder that for 95% confidence interval, our z-star is equal to 1.96. And then we can just plug the rest of the values that we have into the formula that we were given in order to find the minimum sample size to estimate a population proportion. So we plug in our z-star divided by the margin of error, which is 4%, convert that to a decimal is 0.04. Then we square that and multiply that by 0.5, which is our estimate of p. Then we just multiply that by 1 minus 0.5. And after multiplying that together, we get 600.25 as our sample size. So yes, 600.25 is our answer, but it's not really a realistic answer for the problem that we're given. So 600.25 is the minimum sample size. So we should round up to 601 in order to get a more even sample size, because if we had a sample size of 600, that would not be enough to satisfy the 95% confidence interval with the 4% margin of error. So we're going to round up just to make sure that we definitely would get those results with that sample size. So we can say that in order to construct a 95% confidence interval with the margin of error of 4%, we should obtain a sample of at least 601. Okay, so moving on to hypothesis testing, we just did confidence intervals before, but hypothesized test proportion is used when you have one sample with one categorical variable. So the hypothesized value of the population proportion is symbolized by p sub 0 because this is the value in the null hypothesis. So again, we want to check that we have 10 successes and 10 failures in our group, in our sample, I mean. And then we can say that if we do meet those assumptions, that we can use the normal distribution. So if we can use the normal distribution, then our sampling distribution will have a mean of our hypothesized value in our proportion. And then our standard deviation would be equal to the square root of our hypothesized value times 1 minus that same hypothesized value divided by our sample size. So if we do not meet our assumptions, so if our successes and failures are less than 10, then the distribution of sample proportions, we would use a binomial distribution for that. But we're not going to go over that in this. We're just going to go over if you do meet your assumptions. So the normal approximation method formulas, we have a 5-step hypothesis testing procedure that is similar to the ones we've had before. So first we would check our assumptions and write our hypotheses, so assuming that we have at least 10 successes and 10 failures. Then we're going to calculate the test statistic. So the formula for a test statistic here is z equals the sample proportion minus the hypothesized population proportion. And then we divide that by our standard error that we went over in the slide before, which is written there in the formula for you. So after we have our test statistic, we can determine our p-value. And then we can make a decision whether to reject or fail to reject the null hypothesis. And then we can state a real-world conclusion, putting that decision whether to reject or fail to reject the null back into the context of the original problem. So I'm just going to go over an example of hypothesis testing for one population proportion. So is the percentage of creamery customers who prefer chocolate ice cream over vanilla less than 80%? In a sample of 50 customers, 60% preferred chocolate over vanilla. So our first step is to check our assumptions and write our hypotheses. So we do our math and we find that we have at least 10 successes and 10 failures. So that means we can use the normal approximation method. So next we're going to write our hypotheses. Our null hypothesis is p for proportion is equal to 0.80. We'll use 0.80 here because we want to see if it is less than 80%, which is the standardized proportion here in the problem. And we wouldn't use 60% here because that's what we got in our statistic, in our sample statistic. So moving on to our alternative hypothesis is p is less than 0.80 because we want to find out if we're going to be doing a left tail test first of all, and we want to know if the percentage of customers who prefer chocolate over vanilla is less than 80%. So next we're going to calculate our test statistic where most of the math comes in here. So we have our formula in the top right corner there, and we really only need 3 pieces for this formula. So we need our sample size, which is 50, which you can see in the bottom of the problem there, 50 customers. Our p-hat is 0.60 because that is our sample statistic. And then our hypothesized population proportion is 0.80. So we really just need those 3 things, and once we fill those in and do all the math out, we get a test statistic of negative 3.536. So next we're going to determine our p-value based on that test statistic, so we can plug it into a normal distribution and do a left tail test. And we get a p-value of 0.0002031. So we can definitely round up that p-value, but nevertheless we can make a decision, and it is definitely less than our alpha level, which is 0.05. Therefore, we can reject the null hypothesis and state that our data is statistically significant. Then, just putting it back into the context of the original problem, we can say that yes, there is evidence that the percentage of all creamery customers who prefer chocolate ice cream over vanilla is less than 80%. So we just did one sample proportion, and now we're going to do one sample mean. So going back to the central limit theorem, remember that it says that if the sample size is large, then the distribution of sample means will be approximately normally distributed with a standard deviation equal to the standard deviation over the square root of n. Sorry, it's a little far over there. But here in terms of means, we say that a large sample size is one where n is greater than or equal to 30. So here with our sample means, we're going to be using a t-distribution instead of the z-distribution. So the difference between the t-distribution and the z-distribution is really that height varies depending on sample size in the t-distribution. So we're going to go over it a little bit in the next slide. But with confidence intervals and hypothesis tests, we're going to be using the t-distribution when we're working with one mean. So just a little bit more on the t-distribution first before we start. Really what you need to know about it is that the height of it is determined by the number of degrees of freedom. So before you make any degrees of freedom in Minitab or Stackey, before you make any t-distribution in Minitab or Stackey, you're going to be asked to input the degrees of freedom because that really has an effect on the height and the data that you get from that graph. So to calculate degrees of freedom, for one sample mean, it is your sample size minus 1. So it's pretty simple, but you just want to make sure that you always input that so you get the best data for the problem that you're working on. So we're going to start with confidence intervals. So the general form of a confidence interval, we know that, is sample statistic plus or minus your multiplier times your standard error. So going into the confidence interval for population mean, we're going to change this up a little bit. It's going to be the same general idea, but it's going to be different since we have a population mean. So we still have our sample statistic, our x bar, plus or minus our multiplier here is going to be t star. And then our standard error, we're going to calculate that by taking our standard deviation and dividing that by the square root of our sample size. So we're just going to go over a quick example. In a class survey, students are asked how many hours they sleep per night. In the sample of 22 students, the mean was 5.77 hours with a standard deviation of 1.572 hours. Let's construct a 95% confidence interval for the mean number of hours slept per night in the population from which this sample was drawn. So to compute the confidence interval, we first need to find the t multiplier and the standard error. So the standard error here, we can calculate that by taking the standard deviation divided by the square root of the sample size. So first we calculate our degrees of freedom. Our degrees of freedom is calculated by taking the sample size and subtracting 1. So we have a sample of 22 students, so we can subtract 1 from that. So our degrees of freedom is 21. Other than that, this is what we know so far. So our sample size is 22. We have an x bar of 5.77, and our standard deviation is 1.572. So to plug those in to get our confidence interval, we can get our t star. So we get our t star from the t distribution, and our t star here is 2.08. And then all we have to do left is to calculate the standard error. So we calculate the standard error by taking 1.572, which is our standard deviation, and then dividing that by the square root of our sample size, which is 22 here. So we get, after multiplying and dividing that out, we get 0.335 as our standard error. So now we have our x bar, our t star, and the standard error. So that's all we need to calculate our confidence interval. So we can multiply the t star and the standard error out to get our margin of error of 0.697. And then we add and subtract that to 5.77, and we get a confidence interval of 5.073 and 6.467. So we can say that we are 95% confident that the population mean is between 5.073 and 6.467 hours. So we can do the same thing that we did with the sample proportion when we were given a confidence level and a margin of error, and then computing a necessary sample size that will satisfy that. So that formula is very similar here. Here we're going to be using the z multiplier for the given confidence level. We're going to be using an estimated population standard deviation and a margin of error. So we really just take the z-multiplier, multiply that by the standard deviation, divide it by the margin of error, and then we can just square that. And then that will give us a sample size for estimating a population mean. And just remember, if you get a decimal, that you want to round that answer up so that you'll satisfy both that confidence level and margin of error. Okay, so moving on to hypothesis testing with one mean. It's very similar, same 5-step hypothesis testing procedure. We're going to check our assumptions and write our hypotheses. So in order to use the t-distribution here with a mean, the sampling distribution must be approximately large. And approximately large in this case is one that is greater than or equal to 30. Once we have that, we can calculate our test statistic, which is similar to the formula we've been using. Then we can determine the p-value, which we can find using the t-distribution. Then we can decide whether to reject or fail to reject the null hypothesis based on our alpha level, and then state a real-world conclusion. Okay, so we're moving on to our last section for lesson 8, which is on paired means. So in paired means, we have paired data, which is also known as dependent samples. So we can get paired data two ways. So first way is it can involve taking two measurements on the same subjects. So an example of that is if we're calculating the effectiveness of a diet plan. So we can weigh each participant both before and after the diet plan, and then compare the data so we can see how much weight was lost in order to see if it was really effective. Another way we can take paired data is if we take one measurement on each of two related subjects. So related subjects being twins, husband and wife, brother and sister, any two subjects that are related to one another. So when we're constructing our confidence intervals or conducting hypothesis tests with paired means, we compute the difference score for each individual or pair, and then from there the procedures are the same from the sample mean, from the one sample mean before. So here's the confidence interval formula for the difference between two paired means. So really the only difference here from the one single mean before is that we use the subscript d here, which stands for difference between the two proportions. So for example, for our x bar sub d, we would be taking the difference between x bar 1 and x bar 2, and we would be using that in our confidence interval formula. And then the same thing with the standard deviation in the standard error numerator. We'd be taking the difference between standard deviation 1 and standard deviation 2. Moving on to hypothesis testing, we have a little more formulas when it comes to calculating the test statistic, but otherwise it's pretty much the same as before. First, we're going to be checking our assumptions and writing our hypotheses. So here we want to check that our data is paired, and we also want to check that our sample size is at least 30. Once we have that, we can calculate our test statistic. So first, to calculate your test statistic, you're going to want to calculate the standard deviation. After calculating the standard deviation, you want to calculate the observed sample mean difference, and then you can go on to plug those numbers in to the test statistic for dependent means. So once you have that, you can determine the p-value, and you can use a t-distribution in order to find this. Make sure that you know that your degrees of freedom is your sample size minus 1 for the t-distribution. Then, once you have your p-value, you can make a decision whether to reject or fail to reject the null hypothesis. Then state a real-world conclusion. So this is basically everything I just went over in lesson 8. I just put it in one chart. So we went over one sample proportion, one sample mean, paired means, and we went over confidence intervals and hypothesis testing for each. So I hope that this kind of breaks it down a little more, kind of consolidates all the information. It seems like a lot with all the different assumptions and all the different formulas for test statistic, but this kind of, you can see the patterns between the two. So we're going to our first review question. A study of 66,831 dairy cows found that the mean milk yield was 12.5 kilograms per milking, with a standard deviation of 4.3 kilograms per milking. Construct a 95% confidence interval for the average milk yield in the population. So we're going to just calculate the degrees of freedom for this question. All right, so I'm going to go over the answer here. So our answer here is D, 66,830. So we got that because I just subtracted 1 from 66,831, which is our sample size. So that's how you calculate the degrees of freedom. You just take your sample size and subtract 1. So our answer is D. Second question, in the population of Americans who drink coffee, the average daily consumption is 3 cups per day. A university wants to know if their students tend to drink more coffee than the national average. They ask a random sample of 50 students how many cups of coffee they drink each day and found the X-bar equal to 3.8 and the standard deviation equal to 1.5. We are given that random sampling methods were employed. Because your sample size is greater than or equal to 30, we can approximate the sampling distribution using a t-distribution. Calculate our test statistic. All right, so we're going to go over the answer here. The answer here is 3.77. So this is the data that we're given here. I just kind of consolidated. We're given our X bar, which is 3.8, our mu, which is 3. That's in the first sentence. It says average daily consumption is 3 cups per day. Our standard deviation is 1.5, and our sample size is 50 because we take a random sample of 50 students. So that's really the information we need in order to calculate our test statistic. So we're just going to plug it all in. So 3.8, our X bar, minus 3, which is our mu, divided by 1.5 over square root of 50. After doing all that math now, we get an answer of 3.771 as our test statistic. Okay, an educational research study is designed so the participants complete a measure of demonstrated knowledge twice. The researcher wants to estimate the change in scores from the first to second administrations. Data are paired by participant. The researcher subtracted pre-test scores from the post-test scores and found a mean increase of 6.560 with a standard deviation of 3.867 for a sample size of 100. She wants to construct a 95% confidence interval for the mean difference. Here our t-star multiplier is 1.984, so go ahead and construct your 95% confidence interval. I'm going to go over in a quick sec. All right, so if you haven't gotten your answer yet, you can go ahead and pause it, but I'm going to go over the answer now. So our answer here is B, 5.793 to 7.327. So really, here's just all the math we did out. We have a sample mean, our mean sample here, is 6.56. We add and subtract that to our t-star multiplier times our standard error. So our t-star here is 1.984, that was given to us. And then to calculate our standard error here, we just take our standard deviation, which is from the formula from the last problem. So 3.867, our standard deviation, divided by the square root of our sample size, which is 100. So after multiplying that out, we get a margin of error of 0.767, and then we add and subtract that to our sample statistic, and we get 5.793 and 7.327 as our final answers. Okay, so that was lesson 8. So now we're going to move on to lesson 9, which is a lot of very similar to lesson 8. So this is inference for 2 samples, while lesson 8 was inference for 1 sample. So you'll see a lot of very similar things from lesson 8. So we're going to start off similar the way we did last time, 2 independent proportions. So here we compare the proportions in 2 unrelated groups. So we want to make sure that these 2 groups are unrelated from one another. It's also known as a difference in proportions test. So our assumptions here, we have to use assumptions for 2 groups. So we want to make sure that each group, each proportion in each sample size meets our assumptions. So once it meets our assumptions, our sampling distribution is approximately normal, and our standard deviation is equal to the square root of P1 minus P1 times 1 minus P1 over our first sample size. Then we add that to P2 times 1 minus P2 over our second sample size. So we add those 2 together, and then we take the square root of that. All right, so first we're going to start with confidence intervals, and then we're going to move on to hypothesis testing. So if the assumptions are met from the previous slide, the sampling distribution can be approximated using the normal distribution. So here with the normal distribution, our mean is equal to P hat 1 minus P hat 2. And then our standard error is equal to square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. So it's kind of a mouthful, but it's pretty repetitive symmetrical on each side. So we can calculate the confidence interval here by taking our mean plus or minus the z star and then multiplying that by our standard error. So the mean, the standard error are above, and they're listed again in the formula for the confidence interval. So that was a quick confidence interval. So now we're going to move on to hypothesis testing. So you'll see a lot of similar things from Lesson 8 and Lesson 9. So we're going to be using the same 5-step hypothesis testing procedure. And in order to use the normal approximation method, there must be at least 10 successes and 10 failures in each group. So first, we're going to check any necessary assumptions and write our null and alternative hypotheses. So our assumptions is that, again, there are at least 10 successes and 10 failures in each group. And also the two groups that we are comparing must be independent of one another, so they cannot be related or paired in any way. So after we do that, we can calculate a test statistic. And when we're computing our standard error here, we use something called a pooled proportion. So this is different from a difference in proportions. So we calculate the pooled proportion in order to calculate the standard error. So the formula for the pooled proportion is p hat 1 times n1 plus p hat 2 times n2. And then you divide that number by n1 plus n2. So that is our pooled proportion. Once we get the pooled proportion, we can plug that into our standard error formula in order to get the standard error. And then once we get our standard error, we can calculate our test statistic. Here in our test statistic, we will be using the difference between group 1 and group 2 p hat, and then dividing that by our standard error. So then, once we have our test statistic, we will determine the p-value associated with the test statistic. Then we will decide between the null and alternative, so whether to reject or fail to reject the null hypothesis. And then again, stating a real-world conclusion. So just to go over a quick example of that. So we're going to check our assumptions and write our hypotheses. So the counts of our assumptions are all at least 10, so we can use the normal approximation method. So I'm just going to read the prompt out. So the creamery wants to compare men and women in terms of preference for eating their ice cream out of a cone to determine if there is a gender difference. They take a sample of 500 customers, 240 men and 260 women, and ask if they prefer cones over bowls. They found that 124 men prefer cones and 90 women prefer cones. So we checked our assumptions, so we can use the normal approximation method. So now our next step is to calculate a test statistic. So first we make sure that we have to calculate our pooled estimate of p. So once we have that, we calculated a pooled estimate of p using the formula from 2 slides over. We get a pooled estimate of 0.428. Once we get that, we can plug that into our standard error formula, and we get a standard error of 0.04429. So now we have our standard error, so we can move on to calculate our test statistic. So our test statistic is p hat 1 minus p hat 2 minus 0, and then we divide that by our standard error. So we get a test statistic of 3.85. So next we can move on to calculate our p-value. So here we're going to be doing a two-tailed test, and we can multiply the area on one side by 2 in order to get our p-value. And we still get a very low p-value of 0.00011. So we decide that we can reject the null hypothesis because it is less than our alpha level of 0.05. And then we can just say that there is evidence that the proportion of men who prefer cones is different from the proportion of women who prefer cones in this population. Okay, so we just did 2 independent proportions. Now we're going to move on to 2 independent means. So our assumptions here is that if both sample sizes are at least 30, the sampling distribution can be approximated using the t-distribution. So our confidence interval for 2 independent means is x bar 1 minus x bar 2 plus or minus t star times our standard error. So our standard error for 2 independent means is the square root of the first standard deviation squared over the first sample size. And then we add that to the second standard error squared over the second sample size. So here, since we have two different sample sizes, how are we supposed to know which one to use for degrees of freedom? Well, we just pick whichever sample size is the smallest, and we use that one to focus our degrees of freedom on. So if we have two groups, P1 has a sample size of 100 and P2 has a sample size of 200, for example, then we would use P1 sample size of 100 because it is smaller. So our degrees of freedom then would be 100 minus 1, which is 99. Okay, so our 5-step hypothesis testing procedure is very similar here. Checking our assumptions and writing our hypotheses. Our assumptions are that both populations are greater than or equal to 30, and the two groups that are being compared must be independent. So now we have that, we're going to calculate our appropriate test statistic. So the test statistic for two means is x bar 1 minus x bar 2 over our standard error. Once we have the test statistic, we're going to use the t-distribution to determine the p-value. Then we're going to decide between the null and alternative hypotheses, so whether to reject or fail to reject the null hypothesis, and then put the answer back into the context of the problem for step 5. Okay, so I did the same thing that I did at the end of lesson 8. So I consolidated the formulas for confidence intervals and hypothesis testing for two independent proportions and two independent means into this chart. Hopefully that makes it a little easier to understand what's going on for each. Okay, so we use the data in the table to test if there is a significant difference in the proportions who choose split between younger and older players. So here I'm just asking you to specify the hypotheses. All right, so we're going to go over this one now. The answer here is C. So our null hypothesis is P1 is equal to P2 because we want to make we're testing a difference in proportions here. And then our alternative hypothesis is that P1 is not equal to P2. So we choose not equal here because we want to see if there is a difference. We don't want to see if there's greater than or less than. We just want to see if there's a difference between the two populations. All right, so moving on to U2. Using the same data from the previous question, calculate the sample proportion for group under 40 that's split. So just really calculate our p-hat here. Okay, so here we're going to calculate our p-hat. So really doing that, we just take the number in the category divided by the total number in that category. So here we're looking for the sample proportion for the group under 40 that's split. So our category here is under 40. And then we're looking for the number in that category, which is those who split. So the number in that category is 187. And then divided by the total number in that category is 382. So we get a p-hat of 0.49. All right, so use these data to compute a 90% confidence interval for the difference in mean commute time between Atlanta and St. Louis. Here our t-star is 1.648. All right, our answer here is 5.29 to 8.99. So we calculate this by taking our x bar 1, which is 29.11. It's our group 1 mean here. Then we subtract 21.97 because that's the second group mean. Then we add and subtract our t-star, which is 1.648. Then we multiply that by our standard error. So our standard error here we calculate by, we have a big square root around the entire thing, and on the inside is 20.72 squared. That is our first standard deviation. Then our second group standard deviation is 14.23. That's in the next part over. And then we divide each of those by the sample size for each group, which is 500. And then we multiply that out and we get a margin of error of 1.85. We add and subtract that to the difference in our means, which is 7.14, and we get a confidence interval, 90% confidence interval of 5.29 to 8.99.